Hi, everyone. My name is Xiaoshan Zhou. I'm from University of Michigan. The title of my today's presentation is Interoceptive Robotic Agent for Shared Control and Learning, Collaborative Construction Work. So just explain the concept of interoception, which basically means the internal states of a human being. And we are now trying to exert this capacity to a robot, or if we just talk about the intelligence part, we call it as a robotic agent. Um, and today we really want to discuss the path forward for human-robot collaboration on construction work. So first, I personally do think the construction robot helps relieve a lot of health risks construction workers face on field work. Thanks to all the progress of construction robot, the workers can sit behind a screen and just supervise or remote control the robot, and they can demonstrate the task for the robotic arm to execute. And nowadays, the robot become even more intelligent because they can read from BIM to understand the building, and they can automatically generate the path planning and do the tasks. Um, so now we need to rethink about human-robot hierarchy because previously, obviously, the human remains and the position of planning, but just the robot replace all the physical tasks. And now, with the robot becoming more intelligent and they can independently reason and make decisions, um, how when we define the shared autonomy paradigm, I do admit that there is a lot of ethics problems, and the human should always be the part that is responsible. But it doesn't necessarily point to the direction that the humans can override the system whenever they want, because the human may not be always reliable or their decisions are always the best. In fact, if the robot is specialized, they could make more efficient decision making given a global site. Um, and so the problem becomes when the robot should listen to the humans or adapt to the human input, sometimes they should just stick to their own decisions, especially given the situation that they know the human input is not very reasonable or may not be the best solution in that situation. Um, so this is the first part. And the second part of the problem is for the human-robot interaction. If they want to communicate, depending on the modality we use, especially recently people are using more modern modality like BCI, which I also work on a lot in my own research. We know that the coding human intent is not always 100% accurate. So we need to have a mechanism to handle this uncertainty given the miscommunications that possibly happen. Um, and finally, we need to think about after human intervenes, how the robot should recover to its own original plan or to just follow what the human does. This is just like the situation when you drive. Um, you use the Google Map, and sometimes you may choose another path. There could be a mistake, and you want to come back to the original path that it provided to you, or you may know this is a better path, and you want um, the map to replan the road for you. So this is the same situation we have in the human-robot collaboration relationship. So given the problem, I want to share two areas that I am very excited about. The first one is about resilience. I think the ability to recover, adapt, and continue is really important. And more important that we pursue the perfect alignment of human-robot decision making. So here the relationship is not necessarily mean we need to have an emotional bond with the robot, but the resilience borrows a lot from the city resilience research, like how the infrastructure systems respond to or recover after a natural disaster. So that just like the figure shows, if we don't have resilience, it could just fail forever. But it also have the situation that we rebuild. and it's much stronger than before. And obviously, this is what we pursue. Resilience is a very complex concept. In 2022, researchers from all over the world wrote a paper titled Resilience and Active Influence. And there they decomposed the resilience into three aspects: inertia, elasticity, and plasticity. So if you just give a quick review, the inertia means resistant to change, which just quite like what we learned from the physics. And the elasticity means we can bounce back to the side points. The best example is the rubber band. We can stretch away from its normal state, but we know it will return easily without tearing. And finally, the concept of plasticity is a bit complex. So if we put into our own words, I would say sometimes you need to have some redundancy to help you remain flexible, especially in the complex situation. Or we say we have plan A, plan B, plan C. We have those alternatives. So if one fail, we could switch to another. But before we dive to the equations, I want to give you an intuitive understanding. So you could imagine the workspace of the robot. It's a landscape. It has peaks and valleys. And we know the bottom of the valley is the most stable state. So if we put a ball on this landscape, we know the ball will automatically moves to the bottom of the valley because there are many attractors at the bottoms. And the stronger the attractor is, we would call it has stronger inertia that resistant to change. So this is how we construct the robotic workspace. And the human input could be seen as a disturbance, like you shaking the landscape. If the disturbance is small, the ball is still move around in the same valley, but again, it will come back to the bottom. So this is the concept of elasticity. But if the shaking is big, the ball will jump out of the current valley to another valley. So this is what we call as a plasticity. And now we began to construct more detailed math to describe the system. And how the robot constructs the landscape is called the phenotype, which would guide the dominant path the robot takes. And more importantly, we have a concept of marker blanket, which mediates the boundary between the agent's internal states and external environment. So this is an important concept because previously the robot it just perceives the environment and based on the environmental conditions to make their decisions. But now they begin to have their internal states and they monitor their internal states to make the decision. So this just like the human being, we have the biological system. When we talk about the homeostasis and allostasis, and at the same time, the robot will have self-reflection, which means they will reflect why there would be a divergence of their decisions with the human counterparts. Uh, and based on their this self reflection, they will evolve to a meta version, or we call it a more intelligent version. Say this has very close relationships with the memory systems we have, like the encoding and retrieval of knowledge. Memory encoding and retrieval system have a good balance between these two aspects. So we definitely think this could be a better solution based on self-reflection. So just give a summary of today's presentation, we really want to emphasize that learning is not simple imitation, and we need to build resilience in human-robotic collaboration. So this is the references for today's presentation. We gratefully thank for the funding from ISARC. Thank you, and we welcome any questions.